actor-oriented databases like Reactor DB and also Orleans. That's actually promoting this vision of actor-oriented database. So we would like to try to apply this into particular two particular cases and see how we can use that for these cases. So that's the background of this book. Right. So so we look into the particular domain of IoT data management. So there's increasing IoT data being generated from different domains. It's increasing every year. More and more the IoT devices being deployed, like in the home, at governments, and for public infrastructures, and also in enterprises. So a major challenge in IoT applications is that how do we build an IoT data platform that not only query the data, store the data, query the data, analyze the data, but also to support the development of the applications that often has a real-time flavor. So you have to react to the change in the environment, change of the data, and also interact with the user in a real-time fashion. So that's a major challenge. So there's there's already some system that can allow us to do it. So we look into two case studies, and then we look at two particular systems that allows us to build this kind of IoT data platform. So one case study is the structural health monitoring, which is the collaborated research with SHMOP, which is a startup company, which is trying to set up IoT platforms to measure large-scale structures. Like, for example, the Great Bells Bridge in Denmark. So they deploy a set of sensors to detect, to measure the bridge's extension, inclination, and also like the weather conditions, like temperature, wind speed, etc., that will affect the structure. So the aim is to identify whether the structure has any section that has any problems that cause safety concerns, right? So to support this application, they need to gather like a lot of data from the sensors, process the data, and also store the data and generate alerts, and also supporting the engineers then going to the field to interact with the platform. Okay, so that's one case study that we study. Another case is a beef cattle tracking and tracing case. This is a collaboration with the Embrapa. It's a Brazilian agricultural research institute, and also it's a lot of discussions with future cropping, a lot of agricultural expertise that form this future cropping platform. Say organization or project. So a project. Okay, that's mainly Marco's connection. So a lot of the experts actually from CITES, which is it's an organization. Right? So this is an organization from Denmark. It's an agricultural research organization. So the aim of this case is to increase the consumer confidence in the agriculture products. In this particular case, it's a beef cattle. So for the food that they buy, they can trace back to the origin of the food, and also checking where the food is now, right? It's not for the end customer, but for the, like, for example, the transporters, etc. They want to see where they are now, right? And also for the farmer, they want to see where the cow is right now and where they have been, and so on. So for this application, we also need to collect a lot of data from sensors and scanners and so on, and have to integrate this data, right, and process, analyze them, and also interact with the users in real time. Okay, so by doing this, looking into these two cases, we try to summarize a few requirements that are general to all kind of IoT applications, at least from these two applications. So for the requirements of IoT data platforms, the first requirement, of course, is scalability, which is scalable to the number of devices, the number of users, and also the data velocity, which generate more data continuously. And how do we scale the system in order to process them in real time? Another requirement that is quite interesting is that the data platform has to be open and elastic. So it's very often that in an IoT application you have IoT devices come and go, right? And also install new devices. And every time you add a new type of devices, you have to. So the data platform should be able to kind of adopt these devices' data, right? Collect the data, even though the data has different formats or different semantic requirements, semantics, so new processing requirements. Yeah, and also when you have more add and remove devices, you want to scale the servers on the floor. So, yeah. So this third one that we look into is that we'd like the IoT data platform to support both continuous monitoring queries and also interactive queries that has low latency. That's three requirements that mainly we look into and comparing different options. And something that actually I didn't list it here is that, for example, you have complex business processes that you want to have transactions and so on, and that has complicated application logics. That's something that could potentially be interesting, but we didn't look into that so far. So one option, right? So we may look into two options, right? Two obvious options to develop this IoT data platform. One option is distributed data stream systems. Like for example, nowadays you have distributed data stream processing systems like Flink, Storm, and so on. All these systems support a kind of a data flow programming model. You define the operators or the functions that you apply to the streams, the input streams. And this function produce the output stream, and then you apply the next function to these streams. So basically, a data flow program can be compiled into topology. It's a fixed topology. So then you generate output streams. So if we revisit the requirements of that we listed, right, for IoT data platforms, scalability. So these kind of systems are very scalable. So you do state partitioning and do pipeline parallelization. That's actually the system is very scalable. So if we look at open and elasticity, right? So usually these systems provide a predefined topology with stateful operators, and also has a fixed task configuration usually. Right? So we can add, of course, we can adapt these systems to add more adaptivity, but they are not so flexible in the sense that you have if you program the whole program into a data flow. Okay? It's a fixed topology. Then if you for example, you add a new type of data, new type of IoT devices, then you probably change a lot of functions throughout the whole data flow. So it's not so open, it's not so extensible, as least from our experience. So we look at the third requirement. Well, this system usually supports continuous queries. Okay? They are actually designed to target continuous queries, which is good. But we look into interactive queries, like ad hoc queries, like we want to just, for example, engineer goes to the field, to the bridge, and look into a particular sensors or a bunch of sensors. If we want to just query this the current reading of these sensors. There's limited support for that. I'm not saying that's impossible. You can trick the system and somehow make it happen, but it's not naturally supported. If your application has a lot of logics of interactive with the users and other actors, then that would actually quite complicated to implement in a data distributed stream system. So, well, we also look into another option, so actor-oriented database systems. So, for example, the AODB or Microsoft Orleans. So, actor models, so you have heard about that, right? So, the actor models, all the programs can implement it into actors. So, its actors are objects. So, it's like you just write like object-oriented programming. And each actor has encapsulated local states. Then you have like define some functions over these states. That's the actors. And the actors communicate with each other with asynchronous messages passing. Yeah. So the actor process a message at a time. That's which we call basically it's a single-threaded operation. So the vision of AODB is to adding basically many applications use actor system to implement stable ubiquity applications. So the local states of all the actors in the actor systems actually forms a database. Right? So the vision of AODB is to adding database functionality for actor state management. So for example, indexes, transactions and queries and so on to facilitate the application, the programming of applications. So, so for this particular work, we actually look into Orleans, Microsoft Orleans, which doesn't have a relational model. It has only the actor models and arbitrary states. Okay? So in Orleans, they adopt virtual actors, which is kind of concept like a virtual memory. So you can load actors at runtime, right, when it's activated, and when it's not idle for a long time, that will be deactivated automatically by the actor system. And the actor system will do load balancing across multiple servers by dynamically allocating the actors. They also support fault tolerance, so if an actor fails, it will restart actors automatically. And also, they recently added some database functionalities like transactions and indexes and so on. So we just take Orleans and try to build our two cases, right, to see what are the trade-offs and what are the design issues and so on. So that's what we look into, this second option, actor-oriented databases. So we look into the three requirements of IoT data platforms. So AODB is also very scalable. They do state partitioning naturally because that each actor has local states, right? And they do asynchronous messaging, so it's pretty scalable. Also, in terms of openness and elasticity, the virtual actor framework provides this load balancing and cluster management functionality. Okay? It's very elastic. If you have new devices that have new data formats, you can simply add more new actor models, actor types. Right? You implement actor types, add to the system, and then you can process the new IoT devices. And also support in terms of continuous and interactive queries. So basically, an actor-oriented database systems, it's a distributed in-memory object-oriented database. So it's in terms of interactive queries, you can simply submit queries to the actors, right? And then you can get you can query the data within the actors, interactively. So we find it's very interesting to build IoT data platform using AODB. So this paper is about how do we model these applications in these two particular cases, right? How do we model the application and build the AODB, right? So the first question, right? We identify some questions about modeling these applications in AODB, right? The first question is how do we identify actors, right? Which are actors? So the first we want to distinguish actors with objects, right? So in object-oriented computing, so you identify each entity as an object. Right? So in this kind of applications, there are many entities that actually process data, interact with each other, and do the computation. Right? So for example, in the product tracing and tracking application. So you have the slaughterhouse, you have the farmer, you have the cow, you have the collar that attach to the cow to detect the location of the cow, for example, and also maybe tags into tag with the meat carts when you after the slaughterhouse slaughter the cattle, right? So so how do we identify which should be an actor, which should be the object, right? So that's the very first task we have to solve, right? So our experience when we are trying to build this application is that we have to answer some questions, right? So what kind of services should be provided? For example, the cow should provide the service, right? Some service to be provided, for example, for the location of the cow, right? That's a service. And this service should be provided to the slaughterhouse, maybe, because the slaughterhouse want to trace back where this cow is from. Right? And also, the farmer is interested in this service because the farmer wants to know where this cow is. Right? And then, so these are the service. This service that's provided to farmer and also to the slaughterhouse. And the input and the output of each task, right? So, for example, this location of the cow would be the GPS signals of the collar attached to the cow, right? And the output would be the data that would be provided to the farmer and the slaughterhouse. And the fourth question would be like, can these tasks be executed concurrently? Right? So if we have multiple tasks that can be executed concurrently, then probably it's good to model them as multiple actors. So, right. So for example, there's some interesting questions, like in particular for this case, like for example, should the cow and the color sensor be modeled as one or two independent actors? Right? So if we look back into the questions, what kind of services that we are providing? So if we only provide, for example, services of the location of the cow. So basically, the cow and the collar combined together actually offer this service. Right? It's not only by the so there's no benefit of modeling them as two actors. So we can model them as a single actor. So we kind of summarize some general idea about how do we identify actors. So one actor should be designed to carry out a specific task, right? The real-world task, and with the associated logic. So different actors capture actually different tasks, right? Simultaneous concurrent tasks. So that's how we identify actors. So for this case, we actually model, the first model that we come up with is that we have a number of actors, a type of actors. For example, you have the farmer actor, the cow actor providing location services, that receive the color readings and store them locally, encapsulate into the actor, the cow actor, right? And in this particular model, in the first model, we actually model the meat cut as an actor. So after the cows be slaughtered by the slaughterhouse, it generates a lot of meat cuts. So each meat cut, we can actually model it as a meat cut actor with the text and also itinerary kind of attached to this meat cut actor. So later on, I will talk about whether this is really good. I mean, now we identify actors, but is this really, have we solved all the problems? Is there any other trade-offs that we should consider? So the next thing that we actually find is something that we have to be careful is that what's the granularity of an actor state? Right? So if you look at, for example, this example, it's a sensor that usually contains several sensor channels. Right? And we can model each sensor channel as an actor. Right? That's one way to do it. But the other way to do it is that all the sensor channels aggregate together as a actor. So there's actually a trade-off between how coarse-grained the actor should be, how coarse-grained the granularity of an actor state should be. So the more coarse-grained, which means that each actor stays larger, right? So there's less concurrency that can happen, right? And also there's also more heavy computations applied to each actor. So there's a trade-off. And if we have a fine-grained actors, then you probably, if you have a task that needs all of the actors states, then you have to communicate with a lot of actors. So there's a trade-off here. So our finding is that when we design the granularity of actors, it's interesting to just look at what are the tasks, right? What are the services they're providing? So the basic idea is that each actor should represent a functionality of one active entity for which detailed tracking is required. So for example, if you often need aggregates of multiple sensor channels, so it would be interesting to just model this as a separate actor. Right? So otherwise you have to always communicate with a lot of actors and aggregate. So so these are general rules that we find that would be very interesting to consider. So that's the model we built for the structural health monitoring data platform. So we have like the sensor actor, we have the sensor channel actors, and we have also physical sensor channel actors. And from physical sensor channel actors, we have virtual sensor channel actors that actually compute data from the physical sensor channel actors. We also have the aggregator actors that aggregate data from multiple sensor channels to provide data as service. Yeah, so the third question that we actually look into is that what's the trade-off of between employing actors or non-actor objects? Right? Some of the data actually, if we can model as actor, like for example the meat cuts. In the first model that we actually model as an actor. So for example, when the slaughterhouse generates the meat cuts, right? So basically it's generating a new actor, and the actor will the meat cut actor will receive or store the information about the location of the meat cut. And if some actor wants to know the location of the meat cut, they have to send a synchronous message to the meat cut actor, and then receive the message, receive the location of the meat cuts. So that's one model. With this model, actually, if you have very frequent queries of, for example, the MICAT location, then you have a lot of communication with the MICAT actor. There's also a potential concurrency bottlenecks when you have multiple updates and queries running at the same time. So another way to model this is that we can actually model the MICAT as an object instead of an actor. So we can have MICAT as an object contained by all these actors. The slaughterhouse, the transporter, and also the retail shops, for example. So in this case, that the data actually replicated across multiple actors. Okay? So in this case, we have some data redundancy, right? So whenever the MICAT has changed a location, you have to update its data. Okay? For example, when you move the data from the slaughterhouse, send it to the distributor to transport to the retailer shops, then you have you have to update these actors, the objects stored in the actors. So there's data redundancy and also versioning overhead. Right? So an alternative actor model for the beef cattle tracing and tracking data platform is that we can model the MICAT as an object that's shared by multiple, not shared, I mean, so replicating multiple actors. Okay? The retailer actor, distributor actor, and slaughterhouse actor. And so, okay? So there's a trade-off here. So it's not so obvious which one is better. It depends on really on the application itself. Okay, so the last question that we actually look at is that how can we maintain our constraints, right? Enforce constraints in the act, across actors. So let's say we have multiple farmers and we have a cow. So example, if farmer A sells the cow to farmer B, right? So there were several actions or several functions that we have to run. First of all, the farmer has to remove the cow from his own cow list, and farmer B has to add it to his cow list. And later on, if the cow was sent by farmer B to farmer C, right, and the same procedure should happen, and also the cow should be updated about who is his owner. So the question is that if I now submit a query to the cow actor, right? So which farmer owns this cow? Right? Remember this in the actor model, this is a synchronous message passing, right? Which means that these messages are not processed in a certain order. There's no guarantee about the ordering. So if you ask the cow who owns you, right? So it's not so obvious that we tell you the right answer. So how do we enforce the constraints across actors? Like for example, how many cows now? A cow only belongs to one of the farmers. That's not so obvious. So if you ask the farmers, maybe the farmer B and farmer C tell you the same time that you have the cow, for instance. So by looking into this particular case, we find it's important to employ transactions or workflow to update data across actors, so that to ensure the actors are consistent in order to maintain constraints or enforce constraints. Okay, so that's all the questions that we have identified while building these two cases. So we try to implement one of the case using AODB. Right? It's in particular it's Orleans. we use the OLIS, actor runtime, and we use Amazon's DynamoDB as the cloud storage for persistent storage of an actor's states. And then potentially we can also use analytical database systems, OLAP systems, to do decorative analysis of historical data. So we focus on this part. We have actor runtime and also the cloud storage. And we implement this in the particular case of structural health monitoring data platform, which actually transition to start company sandbox. So we run a few experiments to see what's the performance of this platform. Okay. The first experiment that we try to run is that we deploy one single server, right? And then we increase the number of simulated sensors, and we see the throughput, like how many requests per second that the platform can handle. So if we increase until like 1,800 sensors, that's actually the CPU usage already reach 100%. So that's a single server. So if you before the CPU usage reach 100%, the scalability is actually very low. So which means that our platform is quite can support the scaling up. Yeah. So the second experiment that we do is that we try to scale out to multiple servers. Right? So the x-axis here is the scale factor, basically adding servers and correspondingly increasing the number of simulated sensors. Right? So these are scaling both the number of servers and also the number of sensors. So you can see that the throughput actually scaled pretty well, linearly over the number of sensors and also the servers. Yeah. The third experiment that we have done is that to see the latency, right? So what's the latency of accessing a particular sensor, right? Particular actor. So we deploy, we kind of draw the latency percentiles of the raw sensor channel data points for time range requests. So we can see that latency actually, most of the data, like for example, 99% of a request actually is pretty less than a second, right? But there's certain actors actually which has a very high latency. 99.9 percentile is very high.
What kind of concurrency load you have on this? Like, is there any concurrency while doing this?
Yeah, yes, there's all are concurrent requests. So, so if you, I'm not exactly the number of requests in this particular experiments, but there's a concurrent requests. So should not exceed the capacity of the system. So, but still there's some actors has a very high latency. Yeah. So, yeah. So this is also a similar experiment. Also show similar conclusions. Okay, so just to conclude the talk, we studied two cases, right? With these two cases, we explore AODB as a platform to implement, a framework to implement IoT data platforms. An advantage of AODB, a very important difference between AODB and also stream processing systems that actually supports online interactive functions that have low latency. So which actually facilitates scalability and also elasticity. So this actually allows the developers to model entities intuitively as actors. So you don't need to remodel the problem as a data flow program. This also enables developer to write complex logics. So basically, any object-oriented programs you can write in AODB. So there is some further research is needed in AODB in order to improve the support of IoT data platforms. For example, executing and optimizing multi-actor queries. That's not available now. Actually meant by the developers themselves. And also integration with modeling tools. Right? How do we model actors? Right? You have like tools to model objects. Like object-oriented programs, you have the modeling tools, but not actors. And also the support for constraints, enforcing constraints, like the transactions and workflow mechanisms are not so convenient now. It's not fully supported. So more details can be found in our paper. It's actually a lot of our thoughts and experience have been written into the paper. So, thank you.
Do you have any question about the priority?
Thank you for the talk. It put me into some thinking from the very beginning with Nick, because you try to compare the data stream platform as a mechanism to support the IoT infrastructure. And I have never thought that actually the purpose of the streaming. So in some respect, that is not the option. The way that I saw your work progressing is how you can capture the services, which is more traditional database management system challenge, and how this could be potentially mapped down to an appropriate traditional quote-unquote data management system platform. And what I gather out of your conclusion is that we need to have in-memory databases, distributed in-memory databases. And if my understanding and thought is correctly, the next step that you might want to pursue is to compare the actor databases with other in-memory databases, distributed in-memory databases, to see exactly where the bottlenecks and
yes, it's actually a very good question. So basically, because actually Michael said talk about that, right? So what's the problem of like in-memory database, right? So in-memory database, they actually, what they argue is that you can write your program into store procedures, right? So you write your program in store procedures and all the business logics in store procedures, and then, yeah, but not, it's, I mean, it's maybe arguable, but like many people don't like to write their programs into store procedures. There's several reasons, and one reason could be like from the software engineering point of view, is that maintainable, right? Is that extensible? Is that easy to program, for example, programmability, and so on. So it's like a programming.
no, but that
objection.
actually, you see, I was going to ask a question previously. I'm not arguing against the actor-oriented approach. I'm arguing against to the different levels. So the first one, the way that I understood and followed your presentation, is as a modeling mechanism that could potentially map down to any other implementation. And in fact, the diagrams that you show us is UML type of diagrams that capture precisely the power of the modeling. The second part is how do you map them down to the systems? And I agree with Marcus. He never used the data stream at all. You use the data stream. And this is exactly what put me into thinking. Now, playing the devil's advocate, you said that it's much easier instead of stored procedure. In some respect, the actors provide you with a scaffolding to write stored procedures. You brought the issue of aggregators. Again, the aggregators needs to be encoded depending on the type of the data. You have to write the appropriate procedure. So in some respect, it's a stored procedure. What you are arguing is the stored procedures on the disk that has to be retrieved and activated, which in that case I will agree with you.
Mm-hmm.
But the fact that you write in stored procedure, if they reside in memory, they are not per se stored procedures. It's just operators, in memory operators. So I think it's nice if you reach it with at least. We can discuss afterwards.
Yeah, we can discuss.
Some
So from my point of view, is that AODB is just an in-memory database which provide you the actor-oriented programming model. So it's not, I mean, it's just a different programming model of in-memory database. Itself, it's a in-memory database.
So it's
We're not arguing against in-memory database.
I
It's a
agree with
different
you.
programming model.
And since we are talking about this is when we commemorate George Samaras, actually their best paper work in ICT in 1999. It was actually mobile agents that they tried exactly the same line of thinking, how you can move from one database, web database to another and be able to extract the information, query information. So it's interesting that actually
But
we brought
also
this part.
object-oriented databases, you know.
Yes.
Yeah, that is, we were all wearing shorts and sandals when we proposed.
So yeah, I think also if you allow me to do one, let's say it's very interesting approach that you apply this to application domain, because IoT data management solutions is an open topic right now. I'm studying a PhD student actually on this right now as well. So, but we are seeing a lot of temporal and spatial systems, because IoT is like you have this ingestion process. You have velocity is the primitive dimension that generates IoT big data streams, right? So, and how do these come into play? I mean, I understand it's very nice. The modeling framework of actors and reactors is very nice, but how do you cope, particularly with velocity and with time and space dimensions that are adding, you know, this volume actually? Because at some point you have to implement things down in a system that has to be very parallel. That came up in a point also. What is the catch with respect to time? I mean, is there any, because that's going to complicate the issues, right?
So you mean adding that it's a data model, or
Well, basically as a first-class citizen.
Yeah, that's a very good question. So we started implementing some spatial aspects into the actor frameworks. We just recently started, so that you can actually issue a spatial query, KNN, near neighbor, and so on, nearest neighbor. And then time, of course, it's an issue. So basically, we are thinking it's very interesting to extend the actor model with this data modeling and queryability. But I have no good answers.
Mm-hmm.
Yeah. It's made to be like research.
Okay. So maybe we want to add something more?
No, I would say that it would be interesting to see the next step. You show a pipeline of the last part that which actually the actors will be the consolidators, where then this could be the feeders to a data stream processing for doing online analytics. So you know, it's at this point one size does not fit all, but you have this integration of kind of ETL data warehousing as well as data stream management system in a pipeline. And maybe this is the way that you interface the IoT to the rest of the pipeline. It does sort of the ingestion and keeps the state.
Mm-hmm.
Yeah. Yeah. Okay. Thank you very much. Yeah.